Okay, so we're continuing with our network science lectures, and today's topic is graph embeddings. So first of all, what is a graph embedding? The other name for it is graph representation learning. So the idea is that we want to find a way to convert all information that graph contains, and that information about nodes, node labels, edges, various node features, into continuous vector representation. And that's also sometimes called an embedding. So in some sense, we want to find a projection from each node of the graph into some high dimensional space where every node will become a point or a vector in that high dimensional space. And we want to make this projection such a way that find such a projection that will make most sense for us. And we're going to define what do we need to do for that. Now, why do we want actually to do this? Well, there are several reasons. Reason number one is that pretty much most of machine learning algorithms that we're familiar with, they operate on vectors or on data points, which are vectors in high dimensional space. It's very hard to use machine learning algorithm directly on graphs. We looked into two different type of tasks, for example, link prediction and node classification, and we looked into some very specific method design for that. But if you can find a way to represent graph nodes as vectors in some space, vectors that contain all the information about graph that is out there, then you can just use those vectors within standard supervised learning, and then you can, or unsupervised learning, and you can easily do clustering, or you can do classification, node classification, etc., etc. So that's reason number one. Reason number two is, graphs are very large, and you might want to find a way to compress them without the loss of information, or with some sort of controlled loss of information, if that's possible whatsoever. And finally, you might want to visualize graphs. Now, it is actually very hard to visualize very large graphs so that you can, understand the picture. And in some sense, the drawing of the graphs or assigning coordinates to nodes is already an embedding process, right? You're just embedding in 2 dimensions. And so what we want to do, but when we do that, we of course lose a lot of information. So what we want to do is we want to find out how to embed graph in dimension of any size. So here is a little bit more detailed picture. So we have a graph where we have every vertex, and for each vertex, we literally want to find out a vector of some length d, and that's a dimension. We don't know what dimension is the right dimension, such that those vectors contain the information about the node itself, but also probably about its connection. Maybe, connections 1 step away, or maybe 2 steps away, or maybe even more. So we want to encode all the information that is needed to reconstruct the graph, or reconstruct some properties of the graph that are important for us for particular tasks. And so the questions that we have to answer is, okay, so first of all, what properties of the graph structure we would like to preserve when we create this type of mappings, right? Then what kind of dimensionality we should use, right? Vectors can be 2-dimensional to draw things, or 3-dimensional, but you probably for large graphs want much higher dimension. And then of course we want to make sure those algorithms are scalable, so we can actually compute them for large graph. So we're going to talk about those algorithms, graph embeddings or graph representation learning, and we're going to thinking about embedding each node separately. So each vertex, each node of the graph will get its own vector in this representation. Now, that's not the only way to think about graph embeddings. There are other ways. We can think about various granularities when we think about graph embeddings, And again, what we're going to do in this lecture is node embedding. So we're going to embed only nodes, right? And every node will be a point in our high dimensional space, and here it's 2-dimensional. But you can actually think of and come up with the ways to create embeddings just for edges, or maybe you can do it for structures. And if you notice here, there was 3 structures. And so those structures being embedded as a single point, each structure, or maybe embedding for the entire graph if you want to compare various graphs. So all of this are embeddings, but typically when we talk about graph embedding, we mean node embedding, and that is what we're going to talk about today. So here is an example of the graph you have seen many times before, which is a quadratic graph. On the left-hand side, we do have a drawing for this graph, which is in fact a 2-dimensional embedding done through drawing algorithm that assign every node a coordinate. In this case, it's typically sort of a force spring algorithm, thinking about every node connected by a spring and trying to balance them. Unfortunately, that approach doesn't work for large graphs, but for smaller graphs, it gives a very nice picture. On the right-hand side, it's a representation. It's also 2D embedding, different embedding created by another algorithm, where we don't preserve edges, of course, but the points, if you notice, the embeddings of the vertices, it's still the clustering structure is being preserved, right? So all the red nodes next to the red, blue next to the blue, green nodes. So you can actually, it does a pretty good job preserving clustering as a property. So how do we do that? So how do we come up with this type of algorithms? So first of all, the raw adjacency matrix itself that represents a graph can be thought of as an embedding for the graph, because for every vertex, I can take the vertex A. It can be represented as this vector, sort of vertex vector, right, through other vertices. Or I take a vertex E, it can be represented as the vertex vector. So that's an embedding, right? If we have n vertices, then dimensionality of embedding is equal to n, and we're done. Now, the problem is, of course, and of course, yeah, by the way, in this type of embedding, we preserve all the information, right? Because the adjacency matrix and the graph is just a different representation. So we completely preserve the information, but did we achieve anything? Well, not really, because those vectors are extremely sparse, and they're very, very long. If you have a million long, if we have a million nodes in a graph, well, the vector of dimensionality will be a million. And of course, we didn't achieve any compression. We cannot use this for visualization because it's a very large dimensional space. And machine learning algorithm will not really work on this because of very sparse vectors and very, very high dimensionality. So though it is in some sort of embedding, some sort of representation, right? Every node has its vector representation. This is not what we're looking for. We're looking for something a bit more optimal and something that can help us with our problems. So there is you can think of like 3 different classes of methods for graph representation learning. One is where we deal directly with matrices, right? Operates in the matrices, sort of forget that the matrices came from the vectors, just look at the matrices. And then there are several methods. One was called local linear embedding, Laplacian eigenmaps, and there are a couple other methods. Then we can also think there are other class of methods which is based on random walks, and that is when we try to build a representation based on random walks that one does on graph. And the reason is the walk allows us to explore local structure. So matrix factorization, matrix itself contains information about local and global structure. Random walks, they usually tell you a lot about local structure. And then there are the entire class of methods on deep learning with the methods where you just do autoencoders to graph neural networks to graph convolution networks. We're going to talk about today, we're going to focus on matrix factorization. We'll talk about random walks, and we'll touch upon one of the methods from deep learning. Next lecture will be, and next several lectures will be about graph neural networks, various types of graph neural networks. So matrix factorization, like algorithm number one that we want to talk about is called Laplacian eigenmaps. Goes back, well, almost more than 20 years now. And the idea of the method is the following. So we try to find the embeddings, right? And here, the embeddings, those vectors, the coordinates are called y's, right? So it's a vector. It's a vector. And the idea is the following. So we want to make sure that those nodes that are similar, and similarity can mean, lots of things, but for example, similarity can mean direct connections, right? Direct connections. So those nodes that are directly connected, they are also live or embedded close by in the embedding space. So close by, if those are vectors, yi and yg's are vector for the node, embedding for the node I and node j. What you want is that for those in that case, when I and j are connected, yi minus yj is small. Now, Sij, if we take it as their adjacency matrix, it is, and let's say we have unweighted graph, it is 0 if they're not connected, and so we don't care so how far those nodes are, how far the projections are, embeddings. And if they're connected, then in order for this function to be minimal, this difference should be small. And so that's pretty much it. So we want to minimize this functional and find embeddings such that for the neighboring nodes, the distance between embedded vectors yi minus yj will be small. Now, you can actually express this problem as a minimization problem with a Laplacian eigenvector. So if you actually, work through this, take the square, you can show that this is equivalent to this outer product with Laplacian eigenvector. And we want to avoid trivial solution when all y's are the same or zeros. And to do that, we kind of add a constraint on this. And then we find the minimum under the constraint. Well, this is very, very similar to the problem we have seen in the lecture when we talked about graph Laplacian and clustering, Laplacian clustering. And so that's pretty much the same problem when we eventually get a graph Laplacian. And the solution, this minimization, can be found as a solution for eigenvalue-eigenvector problem on the normalized graph Laplacian. And the solution are eigenvectors and corresponding, and we'll take the eigenvector that corresponds to the lowest eigenvalue. They will gives us the minimum minimum values, and they will be our embeddings, right? They will create our embeddings. So that is the first method. The second method, even more straightforward in the sense of understanding. So instead of just saying that, look, we want our vectors to be, our embeddings for the connected nodes to be next to each other, right? The difference, and to have a small difference. We can actually say that, like, look, we can actually imagine the similarity matrix to be not only adjacency matrix, but we can do that too, but also we can actually think about other similarity matrix, like, for example, number of common neighbors or atomic adar, those metrics you have heard about in the previous lecture. And then if we have our vectors, we can actually think about here about the dot product of the two vectors, right? Vector I and vector j. The similarity, it's literally cosine similarity in between those two vectors. And so, you know, if our nodes are not similar, right? And this value is small, then this product is small, and you know that means that the vectors in the embedding space are orthogonal. If on the other hand the similarity is large, you want the vectors to be almost collinear, and that will make the similarity large. And then you can actually do optimization and find those embeddings by optimizing this expression. So that's called matrix factorization. So those two methods operate on the entire matrix. Now, having said that, we can switch to the methods based on random walk. Now, before we talk about those methods, I want to spend a few minutes just discussing sort of where they came from. And that will help us to understand how they work. We'll start from actually the algorithm, which is very famous algorithm today, which is called word2vec. The algorithm that allows to find embeddings for words in language, right? So the idea, you know, overall is similar to what we're trying to do with the graph, except for this is done for the language. And to do this for the language, we consider what we use so-called skip-gram model, and we think about the context in which words are being used. And so, for example, right here, we take a phrase, the quick brown fox jumps over the lazy dog, and let's say we want to think about the embedding for the word brown. Now, the word brown is actually surrounded or is sitting within the context of the words quick, the, fox, jump. And so then we can think about training an algorithm, predictive algorithm, that given the word brown gives us a probability to have the words the, quick, fox, jumps to be within the context, within the neighborhood of the word brown. Right, and then when you have that, when you have this set up, you can actually go through all the sort of words, slide the window, slide the context window through the text, and then you can generate those examples, and then you actually build a predictive algorithm that, given the word, will predict the probability of the words within the context. Okay, so that's called word2vec or skip-gram model. Now, why are we talking about it? And actually how you do this, and then we'll discuss why we're talking about it. So to do this type of modeling, what we actually do is I have shown you pairs of words. And so you can use the first word, well, the embedding, you can use the one-hot encoding of this first word, where x1 to xv will be the words, right? The words on the input. And then you try to predict the word on the output that we use here WISE for. And to do this, you do it with one hidden layer of a neural network. And this hidden layer is going to be the coordinates that we're looking for embedding. So these words are that neural network being trained through the examples I've shown. And during the training, we actually calculate the hidden states, and we calculate, through the hidden states, we calculate the matrices. And then for every word, knowing the matrices, you can actually calculate hidden states. So what does it have to do with random walks? Well, the idea is the following. So when you have a graph and we have nodes on the graph, we can actually pick up a walk and walk it along the graph, going one node after another. So we can explore neighborhoods with a breadth first search, depth first search. But when we do this, let's say here is a random walk we do. We create a sequence of vertices, V1, V2, V3, V4, V5, right? This is the sequence of vertices that we walk through during the random walk. But you can think about the sequence as a sequence of words. And then you can use pretty much all the technique, the entire technique that was used for language embedding to embed nodes in the graph, right? Now, so what are we actually optimizing when we do this type of embedding? Well, if you think about this, we actually, in random walk, we are computing the probability or estimating the probability that starting from node I, you end up on node J, right? So we're computing the probability that starting from node I, you end up on node J. Now, if we think about embedding, and then we have an embedding sort of vector representing node I and vector representing node J, then we can look at their similarity and think of the fact that the product will approximate those probabilities. Now, the product by itself will not do that, but we can run it through standard softmax function, which we denote here as sigma, that will convert our dot product, our sort of cosine similarity between vectors, that will convert them into probability space. And approximately what we do in this case is we're trying to optimize this. We're trying to optimize the difference in between the probability that we see on graph and the probabilities, or whatever we approximate as the probabilities from the embedded space, right? And so then the claim is that if we have a good embedding, then we compute those probabilities either from the graph or from the embedding representation, and they will be very similar to each other. And so that's the idea of random walk method. And that's pretty much what deep walk method is doing. So then the computational pipeline for the deep walk will start with original graph, where you take a graph, and then within this graph, you start random walks. You start from some node, and then you go into another, like one node, another node, another node, get a walk. This node, this node, this node, this node, this node, get a walk. This node, this node, this node, this node, this node, get a walk. Now, of course, one of the parameter will be the work length, but you define it when you build an algorithm. Then you send it through the standard skipgram embedding system, the same way as we did for language. And that will, for each node, it will generate corresponding embedding vector. And of course, you can show them in this latent vector space, embedding space, representation. There is all these names, they refer to the same. And And that's what we get, right? So then we get a graph representation in this latent vector space with the properties that if if we generate a random walk from one node to another, the probability to start from one node and end to another can be approximated through the dot product of the representations, or through the vector that we generated and we created in the space. Now, of course, this is like general concept. We can make, there are many algorithms created based on this concept. One of them is also called node to vec, which is a biased random walk. So it's random walk with somewhat more controllable properties. And the idea is that when we do random walk, we might want to combine two properties from this walk. We want to have some sort of breadth first search type of things, where you can sort of explore local neighborhood of the node to have the local structure, and that's usually done with sort of returning to the previous nodes, so that the making sure random walk doesn't go far out. And also through the depth first part, where depth first is this type of walk when you actually when you avoid visiting the previous node, because in a breadth first search, you always coming back and then exploring sort of the next neighbor. And so to do that, you can introduce two parameters, P and Q, and those parameters, depending on the selection of those parameters, your walk will be either preserved as a local, or can sort of go further out. And those parameters help you to control the walk. And then, of course, when you generated the walk, you go back to this pipeline, and then the only thing you changed is you have a different set of walks for the graph, but then you do the same type of encoding and you get some different vectors, vectors representation. Okay. Finally, there is a third type of algorithms, as I mentioned before. We're not going to be talking about graph neural networks today or graph convolution network, but we'll look at one of the deep learning approaches, which is called structural deep network embedding. And the idea here is to try to combine together this unsupervised and supervised methods, and also use very standard approaches that are for autoencoder. So the idea is that you will have an autoencoder for each vertex. And in order for this autoencoder to work, what you do is you can put it as an input for autoencoder. You can put in your adjacency matrix, A or S. And of course, for the vertex, that really means, seeing its neighbors and next nearest neighbors. And then we try to reconstruct the same matrix. And through going through autoencoder in the middle, you get the representation that is your embedding for the node. Now, the challenge here is the matrix, again, very large, very sparse. So you might not want to just embed them to go right after the matrix itself, especially because the matrix is very sparse, a lot of zeros. So you don't want, so what you can do is you can sort of introduce different costs for reconstructing zeros or reconstructing non-zero elements, because non-zero elements are much more important. And so that is done through this matrix B that kind of modulates that cost. But overall, the idea is that first you actually have and this is the functional that we're going to minimize. At first, you actually want to, have an autoencoder that will look for representation. But then, and since this is a matrix, it gives you a global story. But then what you also want is you want The similar properties that we had, for example, from Laplacian eigenmaps, when we force those nodes that are connected to be embedded next to each other. And so to do this, we actually, for each embedding that we have, we do the additional optimization that is given through Laplacian eigenmaps. And this is done through this addition to optimization function. So here it's the same as Laplacian eigenmaps. These are embeddings that we're getting from autoencoder, and this is our similarity, or this is our adjacency matrix. So, and then the system is being trained to optimize this overall expression. So you can think about actually very, very many architectures, and there are a lot of them exist. But for today, we'll sort of limit to this one. Okay. So these are the methods. Now, how can we actually evaluate the quality? So, we can think about the concept of graph embedding, the concept by itself. So what do? Well, we actually taking a graph and we map it into some representation. And our goal is to have enough information in representation to reconstruct the properties of the graph that are interesting for us. For example, if the interesting property is some sort of similarity in the graph, we need to have a metric that computes that similarity, and that similarity can be, for example, even adjacency. And so we should be able to reconstruct the neighbors, who are the neighbors in the graph, and we should be able to do this through the vector through our embedded representation. So, for example, if we're thinking about direct connectivity, right, like finding two neighbors and making sure they're connected, so it's better be that our embedding vectors are almost parallel in this case, so the dot product is very large. And if our two nodes here are disconnected, well, the dot product of the embedding vectors has to be equal to 0. They should be orthogonal. And this is like if we're looking into this type of property. Now, there might be different properties, but typically that's what we are after. And so the way to evaluate this, to evaluate our embedding, is actually just to compute some property. And again, it can be just the fact that there is an edge exists between nodes I and J and C, if this edge can be reconstructed, or how many edges can be reconstructed from our embedding correctly. So, and that's pretty much what has been done. The results I'm going to show here is from the review paper by Pelage Gayal and Emilio Ferrara. So they looked into several metrics. We're going to take a look at a few of them. One metric is so-called precision at K. This is a very typical metric for information retrieval, where you calculate the fraction of correct predictions among top K predictions. So the idea is we'll go through pairs of nodes and predict and calculate the dot product, literally predict if there should be an edge between them. And for those that have the highest value, those top K highest values that we predict that should have that there should be an edge, we'll compare them against the really existing edge in the graph. And that metric, normalized, for example, by K, or sometimes they normalize it by number of, by K, which is the number of edges that should be there. And then they also use the matrix which has been average precision. Well, they just take this precision, and average it. So it's precision at K, summed over K, averaged. Now they run it on multiple types of networks, from karate network, this is a small network, to pretty large like YouTube network, which is a social network of people of YouTube users, and also networks like AstroPH, which is these are collaboration network in astrophysics. Blog Catalog is a social network of bloggers. PPI is a network of interaction of protein-protein interaction in humans, right? So there's a different type of networks and different size of networks, more than 1 million vertices, 4 million edges here. So they tested the algorithm on these networks. So what do they get as a result? Well, here is the results. Now, on the x-axis, this is really its precision at k. So this is 8, 16, 32, 64. So precision at how many pairs, right? We calculated, and the value of precision. Now, what's interesting to observe is, of course, obviously, the further you go, the more mistakes you make, right? And that's sort of typical for any, information retrieval system. The larger the prediction window, the mistakes you make there. But what I guess interesting is that though not TVEC is quite sort of easy to explain and sort of reliable, it doesn't perform the best on all of those algorithms. What's surprising is how well this structural deep learning performs. If you notice, this is green, it always very, very good, right? Not such a bad performance of graph factorization algorithm. This is one of those sort of similar to linear embeddings, to Laplacian embeddings kind of algorithms. Now, what's surprising is that how bad Laplacian embeddings are, sometimes, but good in other locations. So by looking at this, there's sort of mixed results, though, except for that as DNE as an algorithm, and deep learning algorithm actually outperforms all other methods at the moment. And if you look at the mean average precision, where we measure it as a function of dimension, and dimension here is the dimension of embedding. So of course, the larger the dimension of embedding, the better are the results, right? And that's across sort of all algorithms and all data sets. So obviously, the higher the dimensionality of embedding, the more information it preserves. Now, that is the test of this algorithm on so-called SBM data. It's a stochastic block modeling, so it's generating, it's artificial data. It's generating stochastically, means there's sort of randomness in there, and it is block modeling because it generates clusters of block models. And so, some of them there are sort of clusters within the graph, where communities within the graph where we have a lot of connections between the community and some connections in between. And so if you notice, the algorithm like Laplacian eigenmaps did pretty good job, Hope did pretty good job. That's pretty much, those algorithms did pretty good job, but I guess not TVEC is the nicest separation, because again, we wanted communities, and so this is like literally clusters. As DNA did not bad, but graph factorization that actually performed pretty well on the task of reconstructing graph when it came to recovering communities within the graph. It actually performed terribly bad. So it also brings us, to the idea that, algorithms can perform differently on different data sets, and depending on the task, you might prefer to use one versus the other. So as I said before, we can use those algorithms to compress and store the graph, but we can also use them for various machine learning type of problems, right? And one of them is node classification problem. We talked about it in the previous lectures. Here is an example of node classification tasks done on the data sets, similar to us data sets, which is this block catalog, and PPI stands for, this is a human, data sets for protein-protein interaction. Spectral clustering is sort of traditional algorithm for clustering that we tried before. And then there are several other algorithms, and notice that node to back in this case, outperforms deep walk or others. So there is significant gain in node to back. There is no, we didn't test this, the authors didn't test this on a deep learning algorithm on this, but node to back is actually much better than spectral clustering, for example, which is quite surprising, but that's what you see. So you actually run node to back to do embeddings, and then you actually run simple classification algorithm for classification purposes. The same has to do with link prediction. Now, since we do have since we use node embeddings, right, then a link is defined by two nodes. And so having a node embedding specters, we can somehow construct, and that's the right word here is to construct. We can build an embedding for an edge. And there are various ways to do it. You can actually do like sort of average of embeddings for the nodes that define the edge. You can do concatenations, you can do ADAMR, which is just component-wise multiplication, or you can do various sort of L1, L2 computations. So ADAMR is probably sort of one of the most efficient, again, but that's based on experiments, not theory. And so we can look at the results here. There is, several algorithms for embeddings for for link prediction through embeddings. Again, we do at first embeddings, and then we can do just very simple and straightforward classification for if there is a link or no link. And so there is this methods we looked at, or the metrics we looked at in the previous lecture. And here is an example of using the algorithms, those that we discussed, but with different type of mapping of going from nodes to edges. And if you notice, like ADAMR, and in this case, deep walk does pretty good, and similarly well does node to back on this algorithm, but node to back works also well out there. So it feels like, again, node to back is quite powerful when it comes to finding the representation that later used in machine learning for either link prediction or node classification tasks, but it's not good. Those embeddings are not good for visualization, and they're actually not reconstructing the graph too well. So again, that means whenever you have this type of a problem, you probably need to test various methods on your data and to see what works for you. So to sum up, we looked today at several methods that allows us to do graph embedding, and graph embedding means finding a high dimensional representation for a node. We looked into factorization methods dealing directly with matrices, and so we talked about Laplacian eigenmaps and Hope method, and they have pretty much similar time complexity proportional to the number of edges, but they differ in the information they collect from graphs. So the Lecture13 maps are only looking at the first order proximity, which is nearest neighbors. Hope, on the other hand, actually can look for other similarity type of things. We talked about deep walk and node to vec. Also very similar algorithm in terms of their complexity. We also discussed a bit deep learning as DNA algorithm, which has actually a bigger computational complexity, right? Because it goes through all the edges and all the nodes, so much more computation intensive. So with that, we conclude today, and next lectures we will be talking much more about graph neural networks, sort of in various forms and ways and their usage. All right. With that, thank you very much. Bye.